I think we can get started. Today it's a great pleasure to have Professor Dima Damen to talk at the Vision seminar. Dima is an associate professor of computer vision at the University of Bristol, and she received her PhD from the University of Leeds in 2009. She's currently a fellow in the Engineering and Physical Science Council in UK, where she focuses in automatic understanding of object interactions, actions, and activities using static and wearable visual and depth sensors. Dima is a program chair of ICCV in 2021 in Montreal, and also an associate editor of the journals ICCV, TPAMI, and Pattern Recognition. She was selected as a Nokia research collaborator in 2016 and as an outstanding reviewer in ICCV 2017 and CVPR 2013 and 2012. Amongst a lot of things, Dima has done a lot of amazing work in understanding human activities and defining good representations for actions and object interactions. And she's the lead of Epic Kitchens, which is an amazing and large data set of egocentric videos of people at homes. Looking forward to hear your talk.
Thank you very much for the invite and the nice introduction. And yeah, I think kind of people think that, you list a lot of things that people have achieved. And I can tell you that most of these had happened like in the last 1.5 years. So like your career always starts slowly. And then in one part, you just think, oh, everything is happening very quickly. And part of it has happened because of Epic Kitchens. So I'll start to tell you what I'm interested in and why Epic Kitchens was collected. So I'm really focused on this understanding of people interacting with objects. And that's part of the big picture of action recognition. And that's why kind of I'm talking about what I call object interactions. And mostly I want to look at natural object interactions, of which we haven't had many good data sets. So natural object interactions was the idea of why we want to collect Epic Kitchens. We gave people cameras. We told them, go to your home and collect everything you do in your kitchen for 3 days. Start putting the camera on before you step into the kitchen and only stop it as you step out, and just do whatever you're doing normally, all the way from preparing your coffee in the morning to washing the dishes in the evening. And because of this concept of wearable cameras, you're only seeing people's hands, there were lots of people who were willing to collect this type of data. We only collected from people who are living individually at home. This type of footage, which is footage from wearable cameras, is currently not yet available on YouTube, right? There aren't yet wearable footage and wearable good cameras out there that people are wearing. Maybe GoPro became popular for people outdoors doing sports, but no one yet is wearing cameras at home or on daily life. And I think it's just because the hardware is not there, because if you look at the people in the streets, you see everyone holding their phone and looking at it. And if you're gonna offer them something that's hands-free, I'm sure many people will opt on to use it, but the hardware isn't yet there. So we started with data collection. And if you collect this unstructured data, the hardest aspect is how to annotate it. And so after we asked people to collect, and we said, collect everything, no scripting, we then had to find a way to annotate this footage. And the trick we came up with is borrowed from people who've used movies before to collect good data sets, which is a movie comes with a subtitle. So we asked people to look at the footage after they've done a recording and to tell us what they had collected. This gave us this live narration. That was the only way to allow us to scale into the 55 hours we've collected Epic Kitchens for, as released 2 years ago. From these live narrations, we refined these to collect action segments and then bounding boxes of what we call the active object, so the object only during usage. And currently there are 3 open challenges on CodaLab to do some of the basic aspects like action recognition, but we believe the dataset lends itself to far more interesting questions than the challenges currently defined. Right, so once you collect this footage, then the main aspect is what do you do with it? So we collected this footage in 32 kitchens, and we asked everybody to collect all the data they had. And that's the type of recordings they've given us. So, right, so at each point in time, they would say a sentence that reflects what they had intended. However, once we've started collecting, we realized that anybody who English is not their first language, even if they've been in Bristol or in Canada where we collected for many years, they didn't know the name of a particular item in English. That's why we had to revert to asking them to narrate in their native language, and we went via the route of translating these narrations into English. And then in Amazon Mechanical Turk, we went and refined the start and end time. So from the single timestamp, which is when someone said something, then Amazon Mechanical Turkers decided what is the start and end time. And this is the type of action segments we came up with, and you'll see that some of them are currently overlapping. Right, I will, for some reason, this is not the version that I want to show you. So if you don't mind, I will just switch and I'll come back. Right, so we've done this, right. So after we've collected the initial version, recently we have been collecting an extension. We went to 16 of the 32 people who've collected for us and we asked them to record again. 8 of them had been in the same kitchen, and 8 of them, these are mostly students, so they tend to move around every year. So 8 of them had moved kitchens after 2 years. And we had also 5 new participants. We asked them to collect again, and we got 45 additional hours. That's giving us what we are now calling Epic Kitchens 100, which officially will have a release on the 1st of July, and what we will be releasing the video slightly earlier. Right, so the extension gave us significantly denser annotations. So for example, we had something on average 13 actions per minute, and now with the extension, we have on average 20, so it's significantly denser. On average, we have 23% of the actions overlapping, now we're going to 56%. So this was intended to be significantly denser. One of the hardest aspects of doing Epic Kitchens from free narrations is that we had to take all these free words and group them into what we call minimally overlapping clauses. They're not fully distinct, but they're minimally overlapping. So we grouped something like mozzarella and parmesan into cheese. And despite all this grouping effort for verbs and nouns, we still have 97 verbs and around 300 nouns. And that's the nature of collecting real data. And we have a long tail distribution. The y-axis you see here for both verbs and nouns is log scaled. And the two types, the two colors you're seeing here, so dark and lighter, is what comes from Epic 2018 and what comes from the extension. So this is, you can see how the extension is adding more examples for both verbs and nouns. We're also introducing this, let's say, one level of the hierarchy where we group things like cut and peel and break and crush and divide into something we call split. But that's kind of a way to look at groupings of verbs, but there is a lot to be thought about how to go from, let's say, the fine-grained into a coarser grain. So the data set to be released very soon is about 90,000 action segments compared to what we released 2 years ago, so around 40,000. So we basically doubled the number of action segments and, more importantly, increased the density. We have around 20,000 unique narrations, and we're also releasing some automatic annotations of masks and hands and objects. These are automatic rather than manual ground truth, but we think is better than all the manual things we've done before. Currently, so with the 55 hours released 2 years ago, we have 3 open challenges to close end of the month. The first is the simple action recognition challenge. So that is, given a trimmed segment, you're asked to decide what the verb and the noun is. So this is like the basic concept. And of course, that's not what Epic Kitchen is about. Epic is about untrimmed videos, but the community is not yet prepared to understand what type of challenges we can do with untrimmed videos. And if you're interested, the leading board is still open and people are submitting. We also released some of the leading models like TRN from your end, TSM, TSN. We have models out there that people can try and already have been optimized for best performance on Epic Kitchens. If you're interested in Epic, you can visit the webpage. We also have a mailing list for you to know more about when we're going to release the extensions. Right. So setting this as the base, I'll go back to telling you about why natural interactions and what type of problems are we formed around natural interactions. Some of the things will be done with Epic Kitchens, some had been done before Epic Kitchens, but all these concepts are about object interactions and what we call fine-grained concept of object interactions. There are 4 blocks I'll tell you about. So it looks like a lot of things. I will be stopping for questions after every block. And I'll start by one of the first questions we started asking about object interactions, which is, how well are you doing a particular interaction? The question is, assume we see multiple people performing the same type of object interaction. In this case, rolling a pizza dough. How do I know who is doing it better? And there had been lots of work on, let's say, assessment from video, but it had been focused on things like the Olympics, where you take a video and you try to regress to a score that had been decided by the Olympic Committee. And we hope we don't want to have an Olympic committee for every task, including rolling a pizza dough, but we still need to know who is actually doing it better. Can we relatively assess who has achieved a better performance, regardless of assessing a particular grade? So we start with pairwise annotations. Given Mechanical Turkers 2 videos of the same task, asking whether they believe one is performing that better than the other. And in this case, we're looking at drawing. We really wanted to look at a variety of daily tasks, from drawing to pizza rolling. And if we have a number of people who agree that one person is achieving a better performance, we consider that ground truth, both for training and evaluation. And the method we presented last year in CVPR goes as follows. So you have a typical i3D network that's looking at both the appearance and the motion within a long video. So this is a video of several minutes sometimes. In this case, braiding hair. And we have the ground truth. So we have the belief that one person is performing better than the other. A typical ranking will look at across these videos, maybe average the videos, and then have a ranking loss, and then give a grade to the person. But of course, if you're looking at skill, not every part of the video is as meaningful to decide the skill performance of the person. For example, if you're comping the hair, that probably is not as meaningful for skill than if you're doing the braiding act. And in this case, we wanted to kind of learn that understanding. So we added a typical temporal attention, which is, can you learn to weight these segments by how relevant they are for skill? And we didn't get rid of the average weighting completely. We kept the average weighting because we found that training this temporal attention is more stable if we check that it can outperform uniform. Right? So it doesn't improve the performance, it just increases the stability. After doing all this, we were getting good results, but we realized that it wasn't picking the parts of the video that represents errors with high weight. So the error wasn't really getting a very high weight in the attention, and that was against our intuition. And of course, one of the aspects is that errors don't appear in many videos. And if you learn this with a CME's network, in the typical way you learn ranking, the shared weights mean that this doesn't get picked up with a high weight. So one thing we tried, and that probably was the paper is called the pros and the cons, is to add another attention module. And until now, these are exactly the same. They're just two attention modules. They tend to specialize by adding a loss function that expects one of them to attend to what's good and the other to attend to what's bad. So they tend to specialize via this loss. And that allows us to pick interesting aspects of what's good and what's bad in various tasks. For example, this is what a low skill attention module is picking of a variety of tasks, from surgery to doing origami. And in the origami, for example, it's someone unfolding, right? This is us kind of figuring out what gets picked up and then giving you an understanding of what these low-level attention modules pick. Interestingly, some aspects like stopping or hesitating to perform a task was an example of low skill in something like surgery, but was an example of high skill in something like drawing. That's probably the fascination that people in computer vision have now with machine learning, is that you might not have thought about what you would want the network to pick, but it's picking something that is very intuitive and interesting. Like the same particular feature tends to be a high skill in a certain task and low skill in another. I am not presenting results in most of these papers, but if you're interested in any of the things I'm going to talk about, there is a page per paper with the code, data, and additional results. So how well is the first thing we started focusing on, and skill was one aspect. And another aspect is something we call action completion. And I'll show part of the Ellen show where people are being shown a video and asked to specify whether they believe the person is going to succeed or fail in the task they started to do. So they watch the video and they kind of guess whether the person is going to succeed or fail. And that's the concept of completion here. You've set to perform a goal. Have you actually achieved it? We realized even for some of the data sets that we have been using to train for action recognition, in this case, this is HMDB, and we're training for the act of blowing candles from YouTube videos. Most of these YouTube videos tend to have these poor kids blowing these candles that are never blown away, right? So even towards the end of the video, the person is blowing candles, but the candles don't get blown. And that's the goal we're after. So in this case, I'll show you like orange would be pre-completion, and then purple would be post-completion. In the first act, completion actually happens. So there is a ground truth for when the person believes the candles have been blown. In the other video, even towards the end of the video, the action has not been completed in a sense that the candles have not been blown. And this is a variety of methods we compare, but the intuition that Farnoosh, the student who'd worked on this problem, she's just finished her PhD, had, is that every frame in the sequence should have an opinion of where completion is if it exists in the sequence. And remember, this is not a typical localization task because we don't know whether completion will take place. So it's a combination of classification and localization. So every frame then goes through a CNN and an LSTM that knows the past but not the future. And if the frame believes it is post-completion, it's casting a vote to frames in the past as potential completion moments. So this is combining old style voting with some sort of a deep network. So the frame is kind of classifying itself, but also as a result, casting a vote to frames in the past or in the future. It could also cast a vote with more certainty to when in the past or when in the future. And if you accumulate these votes over time, that's what we used to detect the completion moment. And that allows us to also detect when the completion moment is yet in the future beyond the end of the video. We applied this pair class to a variety of actions, including daily tasks like drinking. We also applied it to sports like jumping, high jumping, and also football or soccer penalties. Recently, we've also published an extension where we got rid of this supervision of when completion takes place. We used sequence level supervision. So we only know whether the whole video has achieved the goal or the whole video is incomplete. So we basically got rid of that additional label. Right, so the first bit I talked about is how well you're performing a task, and we focused on skill determination and action completion. And I'll pause for questions unless you want me to keep going until the end. Hoping someone's still hearing me.
So I have some question about the action recognition part that maybe you came back to the slides on the table side. It's on KSM, TR. My question is that when you're doing action recognition on egocentric video, that is there any new observation that, for example, the network architecture work well on kinetics or some other data set that might not work well in IP kitchen? So it's is there any new observation that using this new data set that can give us some insight on how to design better architecture for egocentric videos?
Right. So typically, you would hope that there is another large-scale egocentric data set that you can pre-train on, but that kind of EPIC currently is the biggest data set that we currently have in wearable cameras. If you read the report we've done on these different models, we realize that, of course, kinetics pre-training helps, but it's not yet ideal. We're still very far from the type of features we're after. So you see that even earlier layers are really changing dramatically during the fine-tuning, if that kind of answers your question. But we're not really in a position to compare some pre-training on wearable cameras to pre-training on fixed cameras.
So actually, so maybe I make my question more clear that because you can see that actually when we training, I mean, actually, I'm the author of the TSM. Actually, you show the result. Actually, when we training the TSM, we found that the result that when we training on kinetic, it never beats the I mean that's when we testing on the kinetic data set, it's very hard for us to beat the performance on using ISND, sorry, But when we testing on the something, I mean on the something data set, that we achieve much performance gain. I mean compared to ICCV, that's this kind of data set gap is very clear because for something. I mean, for something that it's more focused on the object interaction that you possibly you need more temporal modeling, but for the kinetic, maybe the background of the particular object will tell you.
Sure.
So I want to see.
Epic Kitchens is definitely in the same category as something, where temporal models like TRN, multi-scale TRN, and TSM achieve very clear potential advantage over TSN with similar backbones and with similar pre-training. So yes, there is a lot. One aspect though, that something doesn't have, that Epic has, is these overlapping segments. And I don't think we've done a detailed analysis of the impact of these using different models.
I see. Okay, thank you.
So the second type of problems we've been asking is dualities. Can you benefit from multiple data sets, multiple kitchens, or different aspects to learn more data than we have? The first paper we published on this is one I'm very passionate about. We call it dual domain LSTM, and I'll try to show you the motivation. This is not Epic Kitchen. This is two data sets that have also been recorded in kitchen-based environments. One is called 50 salad, one is called breakfast. And one of the goals, let's say, of computer vision is to learn a model that can learn from one and apply to the other, and this multi-view or cross-view concept. We were wondering if that's really a realistic target, because the features that are suitable for one data set are very unlikely to be suitable for the other. But the temporal patterns, the relationships over time, should be useful over different data sets. And that's what we've done here. So an LSTM, or a batch normalized LSTM, typically takes one type of features or one data set and then predicts the outcome. Here, we wanted to learn one LSTM, but from two different data sets. Let's call them the red and the yellow data sets. And the only thing we want to specialize per data set is the batch normalization parameters, particularly observation to hidden and hidden to hidden. We still know at testing whether we're testing data set 1 or 2. The trick is there something useful to pass between these two data sets to learn one LSTM, so one temporal model? And for that, we're stealing ideas from dual domain CNNs. So the input contains examples from both data sets. And our main focus is this cross-contamination parameter that says, should I learn the batch normalization statistics from one data set, or would some examples from the other data set be helpful to learn these statistics? That means we have two contamination functions, which are fully differentiable, and you can train this fully end-to-end to allow the batch normalization parameters to be learned not only from one data set, but maybe from examples of the other, if there is some useful information. And we also can do that over different layers, because you believe maybe the first layer of the LSTM might want to specialize, but as you go higher, as you're learning, let's say, more high-level understanding of the actions, you might benefit more from this cross-contamination. And in this paper, we showed that for a variety of different data sets that we played through, for example, if you train on breakfast and you use that alongside it, you use either 50 salad or MPI cooking, all of these are cooking-based data sets, then this DDLSTM is outperforming pre-training fine-tuning, which is probably the best way we currently know to benefit from two data sets, joint training, or using one data set with one batch normalization parameters. And that is consistent for any pair we had been trying. And perhaps this paper was one of the examples of where the reviewing process improves the paper, Because after we put the paper out the first time, people came back and said, well, we don't think this is useful because you seem to be just benefiting from more data, not from relevant behavior from different data sets. So we went and applied the same concept, taking other data sets which are from a very different domain. So in this case, we're training 50 Salad, but we're training it with 2 data sets that are sports related, and 1 Epic Kitchens that's kitchen related. And not only pre-training fine-tuning does much better, right, than a non-related data set, but this is where DDLSTM really benefits and gives a boost. So that's another evidence that it's actually learning something that's relevant about the temporal aspect of the data set. This is very much fishing in the dark. We really don't know what gets, in an LSTM, it's very hard to figure out what gets passed on between these data sets. But look at the paper for how nicely these different contamination parameters are being optimized over layers. Another thing on duality or on learning from multiple aspects is very much related to Epic Kitchens. And this is to be presented in CVPR virtually in a month's time. In this case, we started with training on 1 kitchen. So we have very much a localized environment. And then if you try to test on another environment, you realize that the feature space is very split, right? So the feature space of the source and the target, they hardly overlap, particularly in the RGB domain. The flow has better overlap, but because we know that flow is less sensitive to the environment, but there is still not perfect overlap between the classes. So we tried to do some sort of domain adaptation, taking it from the typical space where domain adaptation is now being tried, which is images, to video, and asking ourselves what's specific, what's interesting in video. And what's interesting in video is the multiple modalities, the fact that there are maybe more than 1 modality we can benefit from. So in this case, we not only added the typical way to do domain adaptation, which is an adversarial with a gradient reversal layer per modality, we also added a self-supervised loss. This is a loss that can be optimized for the 2 kitchens, for source and target, because it doesn't need labels. It just says whether the segments of flow and RGB are from the same action or from different actions, from the same time location or from different times. So it doesn't need really labels in target. And if this is the space of 2 kitchens using source only, so training on only 1 kitchen, if you only implement the self-supervision on top, you find that the target, which is red, is clustering itself into nice clusters. It doesn't yet have the overlap, but it gives you this nice clusters. And then with the domain adversarial, it gives you better overlap. You can look at the paper for how much improvement you're achieving by adding this self-supervised loss. This is one of the ideas of achieving additional multimodal domain adaptation. And kind of as a highlight, the domain adaptation challenge is going to be added as one of the new challenges for Epic Kitchens, particularly Epic Kitchens 2 years later. Right. The last bit on this duality, and I hope you see the link between these 2 different works, is something we call retroactions. So this is actually from the dataset something, and I can show you a video, and I can ask you to tell me what the action is in a similar way to what Epic Kitchen does, and you might agree that this is someone closing a box. Let's see the video again, so that hopefully you're convinced. So this is a video of someone closing a box. However, this video was never captured. The video that was captured was this. The only thing we've done is we reverse time. And without me telling you that, I hope that I have fooled enough of you to believe that particular video could be used to maybe train a model to learn how to close purely from an example of opening. And this is very different than the concept of arrow of time in the computer vision community, where we believe the arrow of time goes in one direction and never reverses. In object interactions, we hope to show in this work that no, object interactions could be reversible. Many object interactions are reversible. We close and open, we put and take. And of course, there are videos that once we reverse, we get another example of the same class. So you can use these as typical data augmentation. There are also these interesting dualities where when you reverse, you end up with an example of a different class. And interestingly, if you revert examples of that class, you go back to class A. So there is this AB where you can revert time and go to B and then revert again and go to A. And of course, there are irreversible videos, actions that if something breaks, it can never come back. If something falls or the stack collapses, it doesn't build up. But this is not the subset we had been focusing on. In this work, we showed that with zero-shot learning, so in this time reversal example, I'll just show you this confusion matrix, every other class in something here is zero-shot. That means we've never seen a true example of someone covering something with something. We only saw the reverse, which is uncovering. And we trained with these reversals, but we tested with the true videos. So we tested with the actual true videos. And I hope that you can see by looking at the diagonal that there is plenty of potential to look at these dualities in object interactions. And I'll pause for questions on the bit about dualities.
I have a question about the retro actions.
Yes.
So you showed how some actions can, like the dual can represent the same actions, and some of them, the dual will represent the opposite action. Is there any way by leveraging the array level data to figure out which videos are reversible and which videos correspond to a different action or the same one?
Absolutely. So the paper shows two bits. The first part of the video, where we use no semantics at all. We just use the confusion matrix to discover the three types. The invariant, where we reverse and end up in the same place in the diagonal. And interestingly, in this paper, we had to start with a model that's time sensitive. So we had to use TRN. TSN would not give you that, right? And then we discovered these dualities. That was part A of the paper. Part B is where we assumed we know the links, and then we trained for zero shot. It's difficult to combine them, right? Because you can't discover from data and train for zero shot. But the paper shows that you can do both. You can discover purely from data with no semantics, and assuming that you know the links, you can train for zero shot.
Thank you.
I'm hoping I haven't lost you yet, and I haven't overloaded you with plenty of ideas, but I'm keen to show you a variety of topics we're after in fine-grained object interactions. And I'll tell you a little bit now about the works we've been doing with vision and language. And I'll show you an example. And again, I'll ask you, what do you think the action is? And I know some of you are probably apprehensive, thinking that I'm tricking you again. No, this is a video of the action open. And hopefully you can collect lots of examples of the action open. And then maybe we can collect a different action. And let's assume we believe this action is called cut. And in computer vision, we can believe that if we collect enough examples of open and enough examples of cut, we can build a very good discriminator that differentiates between the two. However, in the space of reality, life is harder. And you will end up with examples like this. And I hope that you agree that this is a valid example of open and a valid example of cut. I hope you also agree that open and cut don't overlap all the time, right? Opening the fridge is not cutting. So it's a very interesting aspect of where these verbs overlap. And Mike, who's been focusing particularly on verbs in his thesis, kind of looked at different data sets and found that we have one of two types currently in computer vision. We have data sets where people had selected verbs that will never overlap. And this is what you can use to label your data set. We also have this case where we relate the verb with the noun. And that allows us to learn something like open drawer and differentiate from open bottle. But of course, we don't know what open is, and we can't really scale this to an unknown noun. And in Mike's work, one of the solutions he came up with is to look at multiple verbs as a way to better describe the interaction. So if I say open, hold, and pull, does that give you a better representation of the action? And that was our first attempt, where we basically just labeled the same video with multiple actions by asking Mechanical Turkers whether they would use that verb to describe all or part of that action. And of course, if you have multiple labels, you end up with typically what we call multi-label, which is either 1 or 0. But we also explore this soft assignment. What's the probability that you would use this verb to describe the action? And in this paper, which was presented last BMVC, we showed that this soft assignment is really helpful for retrieval. Basically, you can say what gets turned on or off by rotating, what gets turned off or on by pressing. And this relates something like the tap here with the burner, but also separates the tap at the top and the bottom, because some taps gets opened by rotating and some gets opened by pressing. So this is even finer grained than saying open tap versus open burner or turn on burner. You can use it to query subactions like what's rotating. Even though none of these are rotating only, there is subaction of rotation in them, or there is subaction of holding. This space of multiple verbs is also rich enough to allow you to look across data sets. So you can, for example, look at an example of pulling a drawer and using this representation, say this is similar to open freezer. This was done by over-labeling, but more recently, also in ICCV last year, also Mike was looking at how can this be useful for maybe more general retrieval concepts where you have a sentence and a video, but you also want to understand verbs. So in this work, we use two different embedding spaces. One, a space that embeds verbs, and another completely different space that embeds nouns. So as opposed to embedding the full sentence, we're using the part of speech to separate these spaces. And that had been inspired by our intention to understand what open is, regardless of the action or of the noun. Once you've built these two spaces, and you will find that the same video is going to embed with two different visual representations. One visual representation to encode what verb is it, and another visual embedding for what noun is it. And then you can take these two spaces and combine them to retrieve actions. So you haven't lost the interactions. You're taking the video representation that comes from the verb, so that's the visual, and combine these into an action space. And these have been trained jointly. So you have the noun space, the verb space, or any kind of type of part of speech, and they're also combined to train this joint embedding of actions. And I like some of the examples that looks at the maximum activation in neurons of these embedding spaces. So if you look at the embedding space of nouns and you look at a particular neuron, you'll realize it is the biggest activations for a chopping board, regardless of the act, whether you're washing it or sliding or cutting. If you look at the verb space, you realize that there is a neuron that's looking at opening and closing, also regardless of the object, which is what we wanted to look at to kind of get a finer grained understanding. And you can look at that paper for more details, and I believe the code for this has only been recently released. The last bit of vision and language, and maybe more finer grained understanding, focuses on adverbs. And in this work, we're looking at instructional videos, particularly videos from How to 1 Million. And we want to look at not only what actions take place like turn, but the adverb as a way to describe the type that you will achieve that action. How will you achieve that action? So this is using adverbs to understand how you're performing your turn. In this work, we're starting with the video and with the sentence that describes it. And we've parsed these into actions, which are verbs, and then these adverbs like quickly, rolling quickly. After we parse these, we want to learn an embedding. We want an embedding that not only says this is rolling, but considers that quickly. And in this case, we're modeling this as what we call an action modifier. So a transformation in the space that makes the rolling quickly. And then we want to embed the video close to the representation of rolling quickly. We want this action modifier to be shared across actions. So hopefully we can learn what quickly looks like, regardless of the action. And our life would have been easy if these were well-labeled videos, but instructional videos are only weakly labeled. Well, would be relatively easy, let's say. So in this case, we also had to look at where in the video does the rolling action take place. So in this case, we looked around the time the sentence happens. We collected some I3D features, but we wanted to kind of focus on when rolling takes place. So we use the transformer where the query in it comes from the embedding of the action. So we're using rolling here as a query to find where rolling is in the video, and then embedding this close to rolling quickly, and all of this was trained jointly. And this is some of the results where what you'll see is, so we know it's mixing we're after. We want to predict the adverb. And we've tried this on 6 adverbs: quickly, slowly, finely, coarsely, and I forgot the other 2. So we kind of, it was a restricted set, but we varied the type of actions. So the thick border is going to increase when we believe we've localized the action mix. And then this weighted localization is used to predict the adverb, in this case, quickly. And I think we'll see another example. Oh, there are a few examples. I like the turning one, so I kind of will skip a few, but you can see these videos before. So the videos are already, Hazel had put the videos up. So this is turning quickly. And again, this is a normal instructional video. So you see people, and the thickness of the border will increase as you turn, and then you predict the adverb. It's a small subset, but the first time we're looking at adverbs as a way to understand actions. Questions on videos and language before I give you the final bit on audio-visual understanding.
I have a question on the first part with the
yes.
multi-verb labels, because so in a lot of the examples that you gave, there seem a strong influence of geometry, right? Like if you say, well, I don't know, I open a tab by rotating or open a tab by pushing, right? In a sense that's very much connected to the 3D shape of the tab.
Absolutely, yes.
So have you looked at, is there like a certain connection or something that you could exploit there by maybe having like a depth map and then predicting, is this actually opened by pulling it or opened by pushing it or something?
So we haven't gone that through the way you've talked about it, but we've looked at grasps, right? So we thought grasp types are a very strong link to what we're after. And maybe this can be used to predict grasps, or maybe grasps can be used as input. And we've talked to some people who have considered the concept of grasping. So what we thought is, what's an action? An action is a combination of grasping and then some sort of a motor action. And maybe if we aim to learn or label these, we can get action recognition closer to what robotics people need. That was kind of our intention. We looked at grasping, not at 3D geometry. And after lots of discussions, we realized that the robotics community doesn't have a very good understanding of grasp types, or at least we were not led to believe that we could start annotating grasps in a confident manner. We also didn't believe that we could learn these purely from data. But I believe that the multi-verb representation is probably the closest I have seen in object interactions to make them robot useful. Because I think robots had looked at the grasps, but then there is this other bit, which is you not only grasp, you want to perform the act, right? The rotation act. So you grasp and rotate. But I have to admit, we have not been very successful in finding the right partner to do this.
Okay, cool, thanks.
So I also wanted to ask regarding the separation of like verbs and objects. How important do you think that is to also model the state of the object itself? I wonder if there's like, if you need to do a series of interactions with the objects, maybe it also matters where you start from with the object or where you end, besides the action.
It's a flipped thing, right? So you either think about what the act can do, or you think about what happened to the object, right? We also found, and I think in the BMVC paper, we talked about 2 types of verbs that exist in linguistics. There is something called verb of state and verb of manner. That's what the linguists talk about. So for example, if you are opening a door, right? For tiny little infants or kids, kids that are learning how to open doors, you tend not only to tell them open the door, but you tell them hold the handle and rotate it, right? Until they learn that particular manner. And once they do that, then we never use the manner. We just say open the door. So there is, and the same act could be described by verbs of manner and verbs of state. And at some point we were so excited that this will be, we will basically find different architectures to learn verbs of state and verbs of manner. And I don't know whether we didn't have the right data set or we didn't have the type annotations, but that did not work the way we want. We still believe, so linguistics, people talk about types of verbs, but we haven't managed to kind of map it into something practical. But the paper talks about the performance over these types of verbs.
So it's not clear if a combination of these two types of verbs could improve in like recognition.
It wasn't clear on the small scale things we tried. But I still believe it's always a question of where you want to input the data, right? Is it data driven or is it, but there is evidence in linguistics that there are types of verbs and that we tend to use verbs of state more in writing than verbs of manner. And that's why you never find sentences that say push the door in the writing. You'd say open the door because we focus on the goal, right? But what a robot, let's say, needs is the manner, not only the state. So there is a lot to be done there. And I think we were too kind of pushing for it. We didn't have, let's say, a clear route to showing people how to easily label them, because it's not natural for mechanical Turkers to label the mapping from state to manner. And using a small scaled experiment, it wasn't evident that we need, say, different features, or that we tried something like, is flow related to manner and RGB related to state? So let's say that on the scale we've tried, it wasn't as evident to put that into a perfect experiment. But the paper talks a lot about the linguistics of verbs.
Understood. Thanks so much.
And before I leave you time for final set of questions, I'll quickly tell you about our latest insight into audiovisual. And I know at your end, you've done lots of great work at MIT on audiovisual. And I have to admit that 2 years ago, before we collected EPIC, I used to say, I'm a vision person, I don't do other modalities, until I realized as a person annotating EPIC myself, when I had the audio on, I was annotating more accurately. And I realized that's a so naive aspect, particularly with object interactions, to not use the audio. So Vangelis, also in association with AZ and Arsha at Oxford, started looking at audio for object interactions. And this is slightly different than, say, audio for music or audio for speech, because what we noticed that the discriminative audio occurs at a different time than the discriminative motion or the discriminative visual. And this is one of the examples, and there are many. For example, cracking an egg. So you have the very discriminative audio of the cracking, and then you have the motion, and only finally you see the egg, right, coming out of the shell. Similarly, if you look at someone closing a cupboard, you'll have the motion first, and only later you have that discriminative sound. So inspired by some knowledge of how humans deal with different modalities, we looked at something called temporal binding window. So experimental psychologists have been doing some of these nice tricks where they show people something breaking and then the sound, but they add an unnatural gap between the visual and the sound. And if that unnatural gap is within some sort of a window, people tend to believe that they are the same event. And that's what the brain does. It does temporal binding of modalities. Interestingly, there's also evidence that kids have a bigger temporal binding window than adults. So it's something that we probably refine and learn over time. And in this work, we introduced maybe the most naive way of doing temporal binding, which is having this window, and that window scales over time. And then we select modalities randomly within that window, but then not outside the window. And in this temporal binding window, we can kind of vary the size of this temporal binding window and see the effect. But the, let's say the multimodal fusion is just a mid-level fusion where you have RGB flow, but also a spectrogram. And in this case, it was a BN inception network. And then we have a mid-level fusion with concatenation. And then we are predicting verbs and nouns in a manner that we've been doing in EPIC. It was always interesting to look in EPIC of how different nouns and verbs perform with different modalities. And there is evidence for certain verbs and nouns that audio outperforms RGB or flow. There are cases like eating. This is a wearable camera. So eating is usually out of the viewpoint. You just hear the chewing, or spraying, or turning on and off. Like if you're turning a machine on and off, audio is much better than anything visual. Also, in terms of nouns, there are certain material like napkin or foil paper or the extractor fan, where again, audio is much better than visual. I also always get asked about grapes and blueberry, and it's the packaging, right? The packaging sometimes can be very discriminative. But then when you combine these in the temporal binding window, I'm going to show you some examples, and I will also, hopefully you will hear the audio, and you will see how the audio performs on its own, as well as how the temporal binding window gets the best performance. This is a very good example. We're just hearing, it's pouring water. You can understand why RGB is making an error, right? There is no motion. But also in things like opening fridge. In wearable cameras, the camera is moving with you, so the sound are so clear. I like peeling onion because just closing your eye, you know what the person is doing. And EPIC has been released with this very good GoPro audio that people can utilize. And again, the code, the TBN model and the paper, and the TBN model, where we were not participating in the challenge last year, but it was the second ranking best on the leaderboard. Right. And before I conclude, of course, I get the privilege to tell you about this work. And I hope that in every slide, I kind of listed who the people involved. But this is a biggish team. It's a small team for the type of data set we've collected, but a big team for the type of, let's say, problems we've been focusing on. And everybody in the team is focusing on something to do with object interactions. And I owe them lots of credit that they kind of are on the journey, and they believe on these small problems that might not be currently on the path to what people are doing in many papers in computer vision. But hopefully, slowly, we will make an impact and ask questions that have not been yet asked frequently. And if you want more information, the dataset, the code, and the publications, I keep an active Twitter account, and my webpage has all the papers as well as all the code and models. And I'll come back to the list of topics in case you want to ask about the last part or any of the other parts in the remaining few minutes.
Thank you. Yeah, that was great. A lot of stuff.
Yes, I hope I didn't get you headache. I wanted to kind of show the variety of topics and leave it to you to pick any papers you might be interested in.
Yeah, no, that's great. People has questions?
If you've looked at any of the papers and there was anything that's not obvious, please feel free to email me as well. And we have an email address for Epic Kitchens as a data set. If you have any questions, we kind of keep it monitored actively. So hopefully.
Yeah, for the How Well project, yeah, I like this type of ideas a lot. We had a paper many years ago with Hamed and Carl on
the figure skating.
It was on diving.
Diving. Yeah, I think. Yeah.
And we were using as measure for the skill the ranking that the judges were given to each jump.
Yeah.
Of course, that was before the deep learning era.
Yeah.
So nothing worked really well, but it was better. We were doing better in predicting the skills than just normal viewers. Like if you were to watch a jump, the model was better at predicting the score that the judges will give than a naive person. However, if you ask a professional, they will do better.
No. Yeah. Yeah, I think one of the initial motivations we had is that currently, if you look at any how to do video on YouTube, they get ranked by likes, and that's not always evidence of the skill of the person performing them.
Sure.
So we were hoping for an objective measure of how well someone is doing something in a video. And so we kind of have some videos we've collected, but we also have some YouTube videos. And we thought initially that YouTube videos will only show very high skill, but that's not the case. People tend to put horrible videos on YouTube of bad performance. Of course, they're not easy to pick, but there is enough. Like if you look at 500, you will find 20 that are really bad, which was interesting.
Yeah, no, that's great. That's great. Yeah, I should look at the paper money digital. Yeah, that was great. I'm going to have to leave right now because one of the problems is that there are all these back-to-back meetings. So
absolutely, and I guess I kind of have some one-to-ones later if people have questions. But thanks a lot for the invite again. Yeah, thanks for your time. I hope you
have questions. I don't know. Maybe you can stay.
We'll stay a little bit. Thanks.
Okay, thank you. Thank you for your visit.
Thanks a lot.
Yeah, exactly.
Bye.
Bye.
Thanks a lot. Does anyone
Any
have...
final questions?
I think I have
anyone want to express a particular topic they liked? That would also be nice to kind of hear what people think they like the most.
Just one kind of question about this temporal binding window. I mean, that's really cool. Is there any is there any evidence that it's kind of the length is modulated by somehow? Like, if you say you have a sound of a pen hitting a desk, like, is it shorter than if you have like this water spraying or something?
There is some way of how people model events. However, they don't correspond one-to-one to what you're talking about. So they kind of, so they represent events, because that's what they talk about. They don't talk about actions. They represent events, and they kind of give them different categorizations of how instantaneous, how causal, etc., etc. So that they have categorization, and they say that the binding window differs, but it's not directly mapped to a subset of actions in our sense. So that's why we took only the general sense of it. But there is very strong evidence for this temporal binding in hundreds of papers in experimental psychology. I think the bit when we found that children have a bigger window, that was to me the most fascinating, is that it's a learnable thing.
But is that related with sort of just a lower temporal acuity in audio perception in babies?
So of course, typically papers talk about the speed of light and the speed of sound and the fact that they're different, and that's why you need to start with a bigger temporal binding window. I don't think they kind of give the answer the way you've said it, which is they're less sensitive. They just, you know how experimental psychologists do their experiments. They just modify one thing and test 1,000 times and say it's significantly different. They're very cautious on making, but usually it's triggered by the fact that the speed of light and the speed of sound is different.
Okay, interesting. Oh.
Thanks a lot, everyone, and thanks for the invite. And I hope that you were not annoyed by the fact that I didn't give you tables of results of how we outperform baselines. But if you're interested in a particular thing, I hope you can look at it.
No, that was great. Thanks for not giving any tables.
You're welcome. I find it difficult to follow tables unless I've read a paper, but yeah. You just have to believe me that in all these cases, it was worthwhile experiment.
Thanks a lot. It was great.
I have a few